Lesson 2.5, Complex Zeros and the Fundamental Theorem of Algebra. Many of the things we discuss in this lesson are going to be a review or an extension of things we discussed in Algebra 2. First things first, what is the Fundamental Theorem of Algebra? In its simplest form, it tells us that a polynomial of degree n has n complex zeros. Okay, it doesn't tell us much about those zeros. They could be real, imaginary, they could be repeated, any combination of those. It just tells us if we have a polynomial of degree n, then our total number of complex zeros is going to be equal to that degree. Next, we have the complex conjugate zeros theorem. This tells us that if a plus bi is a zero of f of x, then a minus bi, the conjugate, must also be a zero. Okay? The thing to remember about complex roots or complex zeros, they must always occur in pairs of two. And next, we want to discuss odd degree polynomials. So every polynomial function that has an odd degree with real coefficients is going to have at least one real zero. So what I want you to do is think about why that is always going to be true, applying that complex conjugate zeros theorem we just discussed on the previous slide. Okay, so use that previous theorem to explain and think about why this statement is always going to be true. All right, in our first example, we want to write each polynomial in standard form, identify the zeros of the function, and the x-intercepts of the graph. So we have f of x equals x plus 3i times x minus 3i. If we would FOIL that out, we get x squared minus 3xi plus 3xi, and then minus 9i squared. These middle terms, negative and positive, cancel each other out. So we can rewrite this as x squared. And then you need to recall that I is equal to the square root of negative 1. So if we have I squared, if we would square this, I squared is equal to negative 1. Negative 1 times negative 9 is actually a positive 9. So if we multiply that out and simplify, we get x squared plus 9. Now we have our polynomial in standard form. It is degree 2, so using the fundamental theorem of algebra, we know there's going to be two complex zeros. If we would set our original factored form, set each of these factors equal to 0, we would get x equals negative 3i and a positive 3i. Okay, so our two zeros, negative 3i, positive 3i. And if we're looking at the x-intercepts, if you would graph this quadratic function, it's never going to cross the x-axis, so you can go ahead and graph that on your own and see that. And if we look at our two zeros, these are both imaginary. We have no real zeros, so if there's no real zeros, there's going to be no x-intercepts. So in this case, there's none. We have two zeros, they're both complex, so there are no x-intercepts for the graph. Another example, we have g of x equals x plus 2 times x minus 2 times x plus I times x minus I. Same thing, we first want to write this in standard form, and then we want to identify the zeros and the x-intercepts of the graph. So, starting out, I'm going to FOIL x plus 2 and x minus 2 because those are a difference of two squares. So if you recognize that pattern, you can quickly multiply that out to get x squared minus 4. And x plus I and x minus I, that is the difference of two squares pattern again. If you would multiply that out, the middle terms are going to cancel, so you would get x squared minus I squared. And then recalling from the last slide, if you remember, I is equal to the square root of negative 1. So if you squared that, we have minus negative 1. So we can simplify that down to x squared plus 1. Now we go through, multiply, and FOIL out here. We would get x squared times x squared, x to the fourth, plus x squared minus 4x squared minus 4. Then simplify like terms, we get x to the fourth minus 3x squared minus 4. Now we have a polynomial in standard form. We look at our degree. It's a degree 4, so according to the fundamental theorem of algebra, we're going to have 4 total zeros. If we would set each of our factors equal to 0, we get x equals -2, +2, -I, and a positive I. Those are the 4 zeros for this function g of x. The only x-intercepts are going to be the real zeros, which would be -2 and +2. -I and I, those are imaginary, so we are not going to see those solutions when looking at the x-intercepts of the graph. So I would quickly graph x to the 4th minus 3x squared minus 4 to see what this graph looks like. You should have 2 x-intercepts at -2 and +2. In this next example, we want to find a polynomial of least degree with real coefficients and the given zeros. So we're told that 3 and 2 plus I are zeros to the polynomial. The first thing we need to do is apply the complex conjugate zeros theorem, which told us that if a plus bi was a zero to the polynomial, then a minus bi, its conjugate pair, must also be a zero to the polynomial. So we're told that 2 plus I is a zero, which implies that 2 minus I must also be a zero to this polynomial. Now we need to take each of these and write them in factored form. So we have f of x equals, if 3 is a zero to this polynomial, that means x minus 3 must be a factor. If 2 plus I is a zero, that means x minus that quantity of 2 plus I must also be a zero. And if 2 minus I is a zero, that implies x minus that quantity, 2 minus I, must also be a zero. So this is how we take these zeros to the polynomial and write them in factored form. Right now, I'm sure some of you find this notation, or how we wrote this in factored form, intimidating or confusing. So we're going to rewrite this to make it a little easier to work with. So we have x minus 3. And now I'm going to distribute this negative through. So we would have x minus 2 minus I. And then we would have, if we do the same thing over here, x minus 2 and then plus I. So all we did was distribute that negative through. Now I'm going to regroup my terms that I have inside the brackets. So I'm going to group x minus 2 so I have that quantity, then minus I, and I'm going to do the same thing over here, group x minus 2 together, and then have plus I afterwards. The reason we're going to rewrite it in this form is because we're going to treat this factor of x minus 2 as one quantity. So this is one term, and then we have a second term, so we're multiplying essentially two binomials together. So we have x minus 3. Now we're going to multiply out these two binomials. So I'm taking the quantity x minus 2 times x minus 2, which is going to be x minus 2 quantity squared. Then I'm taking x minus 2 times I, so it's plus x minus 2 times I. Then I'm taking negative I times x minus 2, so I have a minus x minus 2 times I, and then we have minus I squared. So now we have a positive and a negative. These two middle terms cancel each other out, leaving us with x minus 3 times the quantity. Now we need to FOIL out x minus 2 times x minus 2. And if we did that, we would get x squared minus 4x plus 4. And then don't forget, I squared is equal to negative 1. So if we're subtracting a negative 1, we're actually adding 1. combining like terms inside the brackets, and now we can actually use parentheses because we eliminated the parentheses inside the brackets before. We have x squared minus 4x plus 5. And now we just have to go through and multiply all these terms out. So if I multiplied this x through to each term and then multiplied the negative 3 through to each term, I would get this polynomial, and then combine like terms, we end up with x cubed minus 7x squared plus 17x minus 15. You can go through and check and make sure I multiplied that out through correctly and simplified correctly. So this is a polynomial with least degree and real coefficients that had our given zeros that we started with. We have a cubic function, it's to the third degree, so we know there's going to be 3 complex zeros. If we go back to the beginning, we had 3 complex zeros. In the last example, we want to find all of the zeros of the function and then write it in linear factorization. Linear factorization is just meaning we're writing it in factored form as linear binomials. So we have a graph to the right of the function, f of x equals x to the fifth minus 3x to the fourth minus 5x cubed plus 5x squared minus 6x plus 8. We're using the graph as a guide because we're going to use synthetic division in order to break this down into factored form. So we're using the graph looking at what some of the x-intercepts appear to be. It looks like -2, possibly 1, and 4 are going to be the values we use in synthetic division to see if those actually are x-intercepts, if they are zeros. So how we use synthetic division, we have -2. That's what we want to check. And then the numbers I put across the top are the coefficients from the polynomial we started with. So I listed my numbers of my coefficients across the top. Using synthetic division, we always bring the first number down and multiply diagonally. So -2 times 1 was -2. I add vertically -3 and -2 is -5. Multiply diagonally, -2 times -5 gives me 10. Add vertically, -5 and 10 gives me 5. Multiply diagonally and continue that pattern on. And using synthetic division, we get a remainder of 0, which means -2 is a 0 to this polynomial, which means it is an x-intercept. Now we're going to use these numbers across the bottom that we have from our synthetic division. These are going to become the coefficients we use in synthetic division next, and we're going to check whether or not 1 is a 0. So we're checking 1. The numbers across the top are what remained when we used synthetic division before, so we can go through that same process. Using synthetic division, we go through, get a remainder of 0, which implies 1 is going to be a 0 to this polynomial. So now we're going to repeat this pattern one more time and check to see whether or not 4 is a 0 to this polynomial, which it appears to be. The numbers we use in synthetic division are going to be 4 on the outside and 1, -4, 1, -4. Going through doing synthetic division again, we get a remainder of 0, which means 4 is a 0 to this polynomial. So we know 4, 1, and -2 are zeros to this polynomial. So if we're going to write this in factored form, if -2 is a 0, that means x plus 2 is a factor. Then if 1 was a 0, that means x minus 1 is a factor. And if 4 was a 0, that means x minus 4 was a factor. So now we need to determine what remains. How do these coefficients apply to what remains in the polynomial we have left? We started with an x to the fifth. If we use synthetic division, that means this would be a polynomial of degree 4. If we use synthetic division again, this would be a polynomial of degree 3. And we use synthetic division again, so these represent a polynomial of degree 2. So this is 1x squared. I can write this out. This would be 1x squared plus 0x plus 1, which we would just write as x squared plus 1. So in factored form, this would be x squared plus 1. Now, that is not a difference of squares. It's not a pattern we recognize, but we can use ideas of factoring and apply it to x squared plus 1 to break that down even further. At the beginning of Algebra 2, we related the difference of two squares pattern to the sum of two squares. If we have a sum of two squares, we know we're going to have imaginary solutions. So if we put this in factored form, it's going to be x and x. We're going to have plus and minus, just like we did when we had the difference of two squares. The only difference being, since this was positive, we're going to have imaginary solutions. So this would be I and I. So in our linear factorization, the polynomial we started with would be x plus 2 times x minus 1 times x minus 4 times x plus I times x minus I. The real zeros would be negative 2, 1, and 4. The imaginary zeros would be negative I and I. In this lesson, we reviewed many concepts from Algebra 2. Remember that the fundamental theorem of algebra helps us determine how many solutions, how many roots we're going to have to a polynomial. The degree of the polynomial tells us how many complex zeros we're going to have. Remember the complex conjugate zeros theorem. If we have an imaginary zero, those are always going to occur in conjugate pairs, pairs of two. And then you also need to think about how can we use the complex conjugate zeros theorem to explain why an odd degree polynomial is always going to have at least one real zero.